Hello, everyone, and welcome to another session on MLOps here at GitLab. My name is Eduardo, and I'll be talking a little bit about hyperparameter optimization and what does it have to do with GitLab. So it will be a little bit more of a conceptual concept chat rather than talking about something that was done. But it is important to pave the way of to what we're going to do next. So why are we doing this? My role is to explore ML data science use cases within GitLab. So test out our tooling for all the use cases that might come up, or most of them. And hyperparameter optimization is a process within the MLOps lifecycle that is very long and tedious, but that can have great results and can be part of the CI process for machine learning. So we're gonna look over the next few weeks. I'm gonna explore a little bit. What does it look like? What is the user experience? Can our runners do that? And the cool thing about working with hyperparameter optimization is that it kind of paves the way towards AutoML, and we'll talk about this a little bit later. So from the beginning, machine learning model is an artifact that is created from applying an algorithm to a data set that was processed. So you have data set, you perform some processing, so change size, the image size, convert the text, clean up some events, and so on and so forth. And then you apply an algorithm to this, XGBoost, random forest, many more. And then you train both these together, and then you get a model artifact. But both the data processing step and the algorithms that you're going to use, they have configuration parameters, things that you pass on the constructor of the model that will change how it behaves, or the search, or how deep it goes into the data, or just tweaks. And these we call hyperparameters. Some examples that we can see of this, like if you have a neural net, the number of hidden layers that you have in there. If you have a decision tree, the depth of the maximum depth of the decision tree, or how many different cuts you can have over there. On the random forest, the sampling, how many features you're going to use. If you have images, the width and the height of the image can be considered, after transformation can be considered hyperparameters as well. So anything that you pass to change that changes the behavior of the model training, these are called hyperparameters. And the thing is, choosing the right hyperparameter can have as much impact as choosing the right algorithm or improving the data set itself. So it is a really important step of the process, and it yields great results, but it takes a long time to perform. So what you do usually is that you have something called hyperparameter optimization, which is the process of choosing automatically the hyperparameter for the model and for the data. So it goes like this: you rank some trials, you train models for all of these trials. Trials is a group of hyperparameters, hyperparameter configuration that you want to test. You train all of these models, you compare the results, and out of this, you choose the best model. This can be done manually or automatically. And from this, you can see that in the end, at its core, hyperparameter optimization is a search problem. So everything that we know about search problems can also be applied here. So how to rank the trials, how to choose the best trial, when to stop, when to start, so on and so forth. So first step of this is that we can talk about is how to create trials. You have two ways of doing that. One, you can pre-compute all the trials that you're going to test out, or you can do this in a more iterative way. So for the first case, you have, for example, grid search that you have a couple of different parameters you want to optimize for. So, and each one has 2, 3, or I don't know how many. you just test all possible combinations. So you create a huge list of combinations and you test them all. So it's brute force. Random search, similar. You do generate, you might generate all of these lists, but you test at random. The hyperparameters in itself, they come from random distribution. So this reduce, even though you have about the same search space that you had before, now the random search, you select at random which space you're gonna look at. And then on the iterative creation, and for both of this, the grid search and random search, you come up with these values beforehand. So you create all these values and then you test all of them and then you compare the results and then you come up with the best model. For the iterative creation, it's a little bit different. You create a few initial trials, so like seed trials, and then you test them and then you look at the results and then you create new trials. So you create iterations over those. You try to, instead of looking at every parameter, you try to be a little bit smarter on where you're going to. So genetic algorithms and Bayesian methods are examples of this more iterative creation of the trials. And the second step is testing trials. So like I showed before, you have the trials and then you create a model and then you compare the results. But the thing is, you don't know if the trial is good or the results, or it's just that it was a really good match between the data that was used and the trial itself. To improve this, to make it a little bit more, to have a little bit more notion of generalizability and see how it will behave to new data sets, we use something called cross-validation. You take the initial data set, you split into n folds, so 1, 2, 3, 4, 5, and then you train 5 times. So for each trial, you train 5 models. Each one of the models will remove part of the data set and will test on that part of the data set that was removed. That means that you have 5 different performance results that you can now create a distribution of how well does that hyperparameter configuration test. So in the end, during this process, you're gonna train about number of trials times number of folds models. So you can quickly see how fast this grows. And often training a machine learning model is not something quick. It can take hours, days, sometimes seconds perhaps, but it is not cheap. It is not fast, and it's a very tedious process in general. So this is why hyperparameter optimization is important, and why a pipeline, having this as a pipeline on GitLab is also really important, because then it can become part of the CI process in itself. It can, you can create a commit that changes the model, the code for the model, and it already starts the pipelines to choose the best hyperparameters for that. You can already use all the runners that you have. You don't need to use the data scientist or machine learning engineer laptop for that. So that's pretty great. And we need to, but we do need to explore a bit how this use case can will behave with, how GitLab will behave within this use case. And like I said, this is the first step towards AutoML. Why? You can think as the choice of algorithm in itself as a hyperparameter. So one level above hyperparameter optimization. Getting optimization to work correctly on GitLab can lead us to actually be faster at implementing AutoML in the future. So I'm gonna just show a quick example over here that I've created of a very simple hyperparameter optimization notebook. So this is a very small data set, about 10,000 or something rows. And here I create a very simple algorithm, a random forest classifier that will look at this data. And I fit this model. And its accuracy is about 738, and area under the curve is 0.725. So all of this, 1 is the best, 0 is the 0.5 is bad. So what I'm gonna do, random forest, if I open the, I'm not gonna do this now, but if I open the documentation, it has many parameters that I can choose. And these are some of them. So I have a max depth, and I can say here, I'm gonna test out 2, 5, and 10. And then for max samples, 100 and 500, and minimum samples split 2 and 10. And then I'm gonna run a grid search with 5 folds on the CV, and I'm gonna score over accuracy. And then it's gonna run all. So it's gonna fit 60 different models. There are 12 candidates, so 3 times 2 times 2 times 5 over the number of folds. This is a very small data set, so it doesn't really it's very fast. So it trained really fast, but it did run for 60 different models. And then I can check my results, and I can do some plots. So for example, the max depth, I can see that there is the test score increased when the max depth increased. So I can see over here. I can also see over here that for the max samples, it tends to increase as well. And for mean sample split, doesn't really change. Another way of looking at this is to using the hyplot, which is I have here the test score and all the configurations. So all the different configurations. So I can look over here and see that for the high scorers, they were mostly max depth was high, and over here it didn't really matter. So I can see, for example, okay, so if I increase my max depth, where are the results coming in? So they seem to be higher than if I decrease them. Let me see over here. Let me see over here. Well, it broke for some reason. Okay. Let me just regenerate this plot. Live coding is always like this. Okay, it does work. So if I have low max depth, results are generally on the bottom side of the test score. But if I have large, they tend to be larger. So this is another way of looking at these parameters. So this is a very quick example of how this can look like. Up next, this was just a introduction of what hyperparameter optimization is and why are we doing this. So the next step is create a very simple pipeline that performs this job on a CI. So I create a merge request. It already computes automatically the best values and does everything for us. So thanks and see you soon.